The area of the capacitor is the surface area of one plate and is represented by the letter A. Both plates have the same area. Okay? The distance between the plates is represented by the letter D. For parallel plate capacitors, the capacity to store charge increases with the area of the plates. You can imagine if you have a bigger plate, you have more room to put charge on it. It will also decrease as the plates get further apart. That's a little more subtle, and we'll leave that for later. So basically, the capacitance is directly proportional to the surface area of the plates and inversely proportional to the distance between them. Since they're both proportional, we can combine them and find the capacitance is proportional to the area of the plates divided by the distance between them. And recall, D is very, very much smaller than A. Here's a little math and physics trick. Once you have an equation that involves a proportion sign, you can replace that by an equal sign and some kind of constant, known as the constant of proportionality. For capacitors, it has been theoretically predicted, which is good, and even better, experimentally measured and verified that this constant of proportionality is called the permittivity of free space. This shows up in many other places, but this is the first time we're introducing it here. And it's symbolized by epsilon 0, and it's 8.85 times 10 to the minus 12 Coulomb squared divided by Newton meter squared. For parallel plate capacitors, C proportional to A over D becomes capacitance is equal to epsilon 0 A over D. And you can see from this, the greater the surface area, the greater the capacitance, and the closer the plates get together, the greater the capacitance, and epsilon 0 is a constant.